Hello, everyone. In this video, I'm going to talk about what is stable sorting, and then I'm going to uh, explain the notations of big O, big omega, and big theta. So for sorting algorithms, when we say a sorting algorithm is stable, it really means to look at two items with the same value. For instance, let's say in the input, I have, let's say my input is a list. Let's call it L, and this is from 0 to n minus 1. So I have n numbers, and then for location I and location j, these two numbers are the same. So L of I is equal to L of j. And then in the output, in the sorted output, okay, so you can place L of I in front of L of j or L of j in front of L of I. They are sorted. So when we say stable, if L of I is placed before L of j is in the output. For the original one, let me just call it X and Y, because in the output, so it's no longer, so if we still use L to represent the output, then the location may be changed. I'm gonna use X. If X is in front of Y, is before Y, okay? So maybe is before Y, then this is stable. Otherwise, it's unstable. All right, so that is what it means by a stable sorting algorithm. So here's an example. So this A here is my input. So I have 5, 8, 9, 8, 3. So after sorting, I have I have a 3, 5, 8, 8, 9. If this 8 is after this earlier 8, and this is stable. If they have been switched, then they are not stable. Okay, so then we know that we can make insertion. So insertion sort stable. So we can make insertion sort stable using the Python code I gave you last time. So that is stable sorting. That's stable insertion sort. All right. So next we're going to look at the notations of big O. So as I mentioned last time, big O is used to hide details of a mathematical expression so that we only keep the highest term. So the dominating term by getting rid of all the constant coefficients and all the lower degree terms. So that makes it clean. And this is in particular very useful to compare two functions, to compare the asymptotic orders of two functions by only looking at the dominating term or the highest degree term, the term of the highest degree. So as you can see here, the big O notation is used to denote a clean asymptotic upper bound of a function f of n. that make look very messy with a lots of other lower degree terms and lots of nasty coefficients, so that doesn't look clean. For instance, if f of n is equal to this number, and that kind of looks messy, but it has a clean asymptotic upper bound. So let's look at the highest the order term. Now, this is no matter how big this number is, it is still a constant. And so if we single out of this, so this is n log n slash 10, but slash 10 is equal to log n minus log 10. So the highest term is n log n. So then we can use big O of n log n to cover this particular instance f of n. So in particular, this big O of n log n is a set of all functions. Okay, so this is a set of all functions f of n such that f of n is bounded by n log n with a constant coefficient. So f of n is less than or equal to c times n log n for some constant. So this c is a constant greater than 0, positive constants. So then if I replace n log n by g of n, so for any other function, so big O of g of n will be the set of all functions such that g of n is the upper bound of f of n. So we replace this by g of n. All right, so that's what this means here. And then the big zeta notation, if we think of this as upper bound, then the big zeta notation is to indicate the lower bound. So which means that the lower bound, so for instance, big O, I'm sorry, big zeta, big omega here, sorry. So it's a big omega of g of n will be a set of all functions f of n such that g of n is the lower bound of f of n. So what that means is that f of n is greater than or equal to c of g of n. Okay, and so this is for some constant, for some constant c greater than 0, and yeah, so and also when n is big enough. So this is indicates that this at some point this is let's say g of 0 or g of 1, at some point this is very big, infinite or something. So we only make sure this is true for some constant 0, c greater than 0, and for all n greater than some n0. So this is for some, and then for all n greater than or equal to some n0. So starting from the n0, and this is always going to be true. Okay, so that indicates lower bound. And if we want to represent both upper bound and lower bound, and then the notation we use is big zeta. So big zeta notation denotes a function that is both asymptotic upper bound and lower bound of a set of non-negative functions. So this just means that big zeta of G of n is a set of all functions such that f of n is big O of G of n, and f of n is big zeta of G of n, both upper bound and lower bound. All right. So that is the end of this video. Thank you for watching.